This is a video for a new eval board from ISL for a family of programmable instrumentation amplifiers, the ISL2853x and ISL2863x. These instrumentation amplifiers feature programmable gain capability internal to the IC, and is also using zero drift amplifier technology to build these instrumentation amplifiers. Let's take a look at what's inside this instrumentation amplifier. It is built off of the 3 amplifier topology. As I mentioned earlier, it integrates the gain resistors to this instrumentation amplifier and uses a digital control interface to program the gain using 2 digital input pins. Another addition to this instrumentation amplifier, as you can see on the bottom, is an uncommitted extra op amp, which provides flexibility on this chip. This op amp is uncommitted, so you can use it for any other purposes that you would like. This amplifier is for the ISL2853x family. The other part in the family is the ISL2863x. And looking in this chart right here, the only thing different is we've taken what was the uncommitted amplifier in the ISL2853x family, and we've integrated it into the instrumentation amplifier path. And what this gives you is basically a fully differential amplifier, where you have differential inputs and a differential output. So the family of ISL2863x amplifiers are ideal for driving high precision A to D converters with differential input front ends. As I mentioned earlier, some of the benefits of this instrumentation amplifier is the zero drift technology used to build this in-amp. Looking at some of the key spec advantages for this amplifier, some of the highlights are very low input offset voltage of 5 microvolts, very high precision gain accuracy in the gain set resistors that are internal to the IC, and very low noise due to the zero drift technology. The other feature, as I've mentioned earlier, is the programmable gain of this amplifier. Using 2 digital inputs, we have a 9 gain selection state. Depending on the part number of the amplifier for the ISL2853x and the ISL2863x, the gain ranges can be anywhere from 1 to 1000. So in this video, I'm going to be talking about the eval board, which I show right here. Everything is populated for you to easily test out this IC. The gain setting switches you see are right here. They're 3-state switches, so high, low, and switch open. You got your inputs to the instrumentation amplifier on your left, and the outputs to the instrumentation amplifier on the right. Power supply connections at the top. And for the family of the ISL2853x, this is the uncommitted amplifiers for the input and outputs. If you look on the back of this amplifier, the gain set table for the device is on there, so that you can easily configure the switches on the front to get the gain settings that you want based on which part you're using, so that you always have it on hand, that you know how to quickly set the gain of the amplifier that you need. Alright, what you see here is I have the eval board powered up with a bias of plus or minus 2.5 volts on the power supply. I'm putting in a signal of 50 millivolts peak to peak into the amplifier, and what you see here on the oscilloscope is the input signal in yellow of 50 millivolts peak to peak, and at the output in blue. And then I can change the gain of these switches to program the gain of the amplifier that I want to put it in. If I change the XY scale at the highest gain of I'm using the ISL2853, so the maximum gain is 100 for the signal. So you can see I can dynamically program the gain with the two logic inputs. So this eval board is fully populated. It's very easy to use. Some of the key applications for the ISL2853x and ISL2863x family of instrumentation amplifiers. One commonly is for bridge type applications where you have a bridge circuit and you're trying to amplify the signal on one leg of the bridge. Most commonly these bridge circuits would be for a strain gauge or a flow sensor. And in fact, in this what you see right here is a dedicated reference design for a 24-bit strain gauge front end amplifier. If you're interested in this reference design, you can actually find more information. There is an app note written for it. It is application note 1853. Another typical application for an instrumentation amplifier is high side current sensing. So in this block diagram, what you see here is one of our integrated FET buck regulators, the ISL8024, acting as a DC to DC power supply, in this example for an FPGA or an ASIC. So you have 3.3 volts coming into the buck regulator and then 1.2 volts coming out, powering the low voltage FPGA. If you want to measure the power consumption of your FPGA, you can implement this solution with a high side current sense using a very low value sense resistor. In this case it's 1 milliohms. Now 1 milliohms will not give you much of a voltage drop, but at 4 amps of load current, and given the fact that these amplifiers, these instrumentation amplifiers, are built with zero drift technology that enable very, very low voltage at the input because of the low noise performance of the amplifier, you can accurately measure the current sense signal using our ISL2853x or ISL2863x instrumentation amplifiers. And in the case of resistive current sensing, especially at high currents, one of the concerns is the power loss of the current sense resistor. Well, if you're going to use a 1 milliohm sense resistor, even at 4 amps of full load current that this ISL8024 can deliver, that is only 16 milliwatts of power dissipation within the sensing resistor. And if you notice earlier, I give the noise performance of the amplifier 0.1 hertz to 10 hertz. So for low frequency, this thing has 250 nanovolts peak to peak of input noise. Well, you can sense down to a very low range of 10 milliamps across 1 milliohms, and that gives you 10 microvolts of a DC signal. That is above the noise floor of the input stage of the amplifier. Because this amplifier is built with zero drift technology, it has very, very low noise at the input. So to conclude the video, again, here's the picture of the eval board. Everything is integrated on this board for you to easily evaluate this IC. Again, just to reiterate, it's a programmable gain amplifier, so these switches will set the gain of the amp from anywhere from 1 to 1000, and on the back you can find the table to set how to set the resistors to set the gain of the amplifier. And then if you need more information, there is a user guide for this eval board. If you go on Intersil.com and look up application note 1880, you will find the user guide for this. It contains the board schematics, board layout, and the BOM to build the board. Thank you very much.